Welcome to this lecture series in general topology. In this lecture, we'll see the connection between bases and continuous functions. By that, I mean, suppose you have a topological space and you're able to find a basis which generates that topology. The job of showing that a given function is continuous becomes a little bit simpler if you understand the basis well. Anyway, all the details will follow, but let us recall what we need. So we will need the notion of a basis. Let me not recall the definition. Then we need the notion of, or rather, we just need to know a key fact about topology generated by a basis. So topology generated by a basis is just that. It is the intersection of all the topologies that contain that given basis. But the key fact is, the open sets under that topology are precisely those sets which can be written as the union of some of the members of this chi, of the basis. So this is the key fact about topology generated by a basis. And then we discussed the standard topology on Rn, which was the topology generated by either you could take this basis, the collection of all the balls in Rn, with centers at arbitrary points and arbitrary radii, but the distances were measured according to the Euclidean metric. Or you could do the same thing with the infinity metric. And there was an exercise which asked you to show that the same thing is true even for the L1 metric, so to say, L1 distance. When I say metric, I just mean distance. So we saw that the topology is generated by all these three bases, this one, and that one. The topologies generated by all of them are the same. So therefore, or not therefore, but I mean, whatever is that topology, we call it the standard topology on Rn. So there are at least three ways of looking at the standard topology on Rn. Choose whichever distance you like, L1 distance, the Euclidean distance, or the infinity distance, whichever is more convenient in the context. Okay, then we need to know what is meant by continuity at a point. So if we have a function from topological spaces, from a topological space X to a topological space Y, and suppose we have a point in the domain, let's call that point X0, and its image is, let's say, Y0. So Y0 is equal to f of X0. When do we say f is continuous at X0? We say f is continuous at X0 if, whenever we choose a neighborhood V of Y0 in the target, meaning in Y, there is a neighborhood U of X0 in X, of course, such that U maps inside V under F. So that was the definition, and we gave a lot of motivation behind that. Okay, then we need to know what is meant by global continuity. So again, suppose we are given some function from a topological space X to a topological space Y. When do we say it is a continuous function? We just say it is continuous if it is continuous at every point in X. Okay, but there was an interesting result or interesting observation that we made, is that f is continuous. A function f from a space X to a space Y is continuous if and only if the pre-images of open sets in Y are open in X. Right? That was the criterion for the global continuity of a function. Let me just rehash what this means. It just means that whenever you pick V in the topology on Y, then this guy is in the topology of X. That's all. Alright, so let us proceed. Here are some problems for practice. And now let us get started. Okay. So here is our first lemma. Let X be a topological space, and let B be a basis for the topology on X. So what does that mean? It just means that the topology generated by the basis is same as the given topology, same as the topology on X. So X was a topological space, meaning X was a set equipped with the topology. This thing came with the topology, and this line just says that suppose you are able to find a basis which generates the same topology as X. Of course, this can also be taken as the topology itself. The topology itself is a basis, and it also generates the same topology as itself. So you can take a trivial thing here, but the usefulness of this lemma is when you are able to locate a basis which is convenient. Okay, so fix such a thing. And now let Y be another topological space and F be a map from X to Y. Okay, and fix a point in the domain of F. Okay, with all of this setup, the following two statements are equivalent. The first is that F is continuous at X, and the second is if V is a neighborhood of Fx in Y, of course, then there is a basis element such that it contains X and its image is contained in V. So let's draw a picture and try to understand what this statement is saying. So we have the space X and we have the space Y. The statement says that whenever we choose a neighborhood of Fx, call it V, there is some basis element which contains X and whose image under the map F is inside V. What does this say? It says that there is a neighborhood of X whose F image is inside V, but the second statement is saying a little bit more. So, okay, I hope you understand the statement. And now we can start proving it. Okay. So, assume 1. We want to prove 2. So, to do that, let V be a neighborhood of Fx in Y, and we want to show the existence of a B. Now, by continuity of F at X, we know that there is a U, there is a neighborhood U of X in capital X such that F of U is inside V, right? So in pictures, there is some U containing X such that F of U is inside V. Now, here is the point. Since the topology on X is same as the topology generated by the basis, every element in the topology is the union of some elements of the basis. Because what is the topology generated by a basis, as we recalled? It is the collection of those sets, precisely those sets, which can be expressed as the union of some of the members of the basis. So every element of the topology is a union or is the union of some elements of the basis, and therefore there is a basis element which is inside U and which contains X. Because this is the union of some of the basis elements, there has to be one basis element which contains X and is contained in U. And that will map, so just call that basis element B. So that is called, just call that B and that's it. So B will satisfy the requirement of the second statement. So I'm not writing the textual details, you can fill it up. And 2 implies 1 is an exercise, it's even easier. The main point here is just that, notice, every basis element is an open set in the topology on X. That's all. It's a trivial observation, but that is all. That's all that you need to prove this. And obviously, you will need to use the definition of continuity. Okay, very simple statement. Let's proceed. Okay, so this time we again have a topological space X, and we have a basis for the topology on X. The meaning of it we have discussed in the previous slide. And let Y be a topological space. Let Y be another topological space. When I say another, I don't necessarily mean different from X. It could be same as X. I just wanted to emphasize that this is one more topological space. And let C be a basis for the topology on Y. So we have a description, or we have a basis for the topology on X, and we have a basis for the topology on Y. And let F be a function, and X be a point in the domain. So that is the setup. And now here is the statement that we want to prove, that the following two things are equivalent. The first is that F is continuous at X. And the second is, if C is a basis element for Y, or C is in script C, and it contains Fx, then there is a B in script B in the basis of X, such that X is in B and F of B is contained in C. Okay, it's a little bit of it's in the similar spirit as the previous lemma. In the previous lemma, we did not have any basis on Y or anything. This time we also have a basis on Y, so this is a natural version of the previous statement. All right, so let's get proving. So for 1 implies 2, assume 1. So let me draw a picture also. Assume 1, we want to show 2. So fix a basis element fix an element in C, and with the property that it contains Fx. Okay. Then in particular, this is a neighborhood of Fx, because the topology generated by C is same as the topology on Y. In particular, every element in C is open in Y. So this is in particular a neighborhood of Fx. This is a neighborhood of Fx, and therefore by the previous proposition, there is a basis element B such that X is in B and F of B is contained in C. So 2 holds. So 2 holds, and now for the other direction, assume 2. For 2 implies 1. Assume 2, we want to show 1. So we want to show that F is continuous at X, given the hypothesis of 2, or given the assumption that 2 holds. So to do that, what is the definition of continuity? We just pick an arbitrary neighborhood. We be a neighborhood of Fx. So I think it's a good idea to again refer to a picture. Here, let me transport the picture, because this is corresponding to the first part. And for the second part, I'll draw another picture. And maybe just explain the thing in words. So we have an arbitrary neighborhood V of Fx. We wanted to show that F is continuous at X. So we pick an arbitrary neighborhood of Fx, and we want to show there is a neighborhood U of X whose F image is inside V. Now again, since the topology generated by C is same as the original topology on Y, V is the union of some of the elements of script C. And therefore, we can locate some element of C which contains fx and which is contained in V. So there is some capital C. The picture is all hodgepodge, but I hope you follow. So there is some capital C in script C which contains fx and which is contained in V, right? And now by the assumption that 2 holds, there is some B in script B whose f image is inside C, right? But if its f image is inside C, its f image is also inside V. Lastly, any element of script B is also a neighborhood of any element of script B that contains X is also a neighborhood of X, because any element of script B is open in X. And therefore, we have located a neighborhood of X whose f image is inside V. That's all we needed to show that f is continuous at X. So I've said it in words and showed it in pictures, and you should be able to write it down now. So I am not going to write all the details. Okay. And now something very interesting will happen. With all these things that we have done, we can establish the Epsilon-Delta criterion for continuity when we are concerned with the Euclidean spaces. So recall the standard topology on Euclidean spaces. You pick your favorite distance. Either you take the 1 distance or the 2 distance or the infinity distance. The collection of all the balls with respect to either of them forms a basis on the given Euclidean space, and the topology generated by them happens to be the same. That is what we showed. All the 3 bases generate the same topology, and this common topology is called the standard topology on the Euclidean space. Okay, so now what we are going to show is the following. We are given a map between 2 Euclidean spaces of different dimensions, possibly. It could also be that n equals 1 and m equals 1, and whatever we are going to say will boil down to the usual Epsilon-Delta criterion that we learn in real analysis. So it is a true generalization. Okay, so we have a map and a point in the domain has been given. Then the following 2 things are equivalent. The first is that f is continuous at the given point. And the second is the Epsilon-Delta thing. For all epsilon greater than 0. So before I even write this, let D denote D1 or D2 or D infinity. Whichever one you pick doesn't matter. So let D denote that, and then the following are equivalent. First is that f is continuous at P. The second is that for all epsilon greater than 0, there exists delta greater than 0 such that whenever we have X in this ball of radius delta around P, we have f of X is in this ball of radius Fp around of radius epsilon around Fp. Or in other words, we can also say, just writing it differently, that x minus p, or the distance, I shouldn't say x minus p, the distance between x and p less than delta implies that the distance between, what have I written? This is just d. Distance between fx and fp is less than epsilon. And you should notice that when n and m are both equal to 1, so that f is a function from reals to reals, then this is precisely the Epsilon-Delta criterion for continuity as we learn in real analysis. Because there anyway, all of these 3 distances are the same. They are just simply the absolute values of the difference of the 2 entries that you feed to the distance function. And then this just becomes the Epsilon-Delta criterion that we learn. Okay. So I hope you appreciate the importance of this. And with that, let us try to prove it. It's basically just an application of the previous proposition. All right. And yeah, so we will use the previous proposition. So maybe I should draw a diagram. Here is Rn, and then on the right side we have Rm, and we have a function. Maybe I'll draw a little bit bigger. Okay, so assume 1, and we want to show that this holds, so fix an epsilon greater than 0. And now we want to show the existence of that delta. All right, so let Bm be this basis on Rn, which is all the balls of some positive radius around all the possible points. This is n, and then we have Bm. Maybe just to change notation, I'll write a y. Okay, so this is a basis for the topology, for the standard topology on Rn, and this is a basis for the standard topology on Rm. And therefore, by the previous proposition, the continuity of f at the point P is same as the following. Whenever you choose a basis element, here containing Fp, there is a basis element which contains P whose F image is contained here, right? So we'll just use that. So let or not let, I mean just define C is equal to this ball of radius epsilon around Fp. I'll draw it. That is C. And now by the previous proposition, we know that there is B in the basis for Rn such that B contains P and the F image of B is in C. Okay. So there is some basis element here. It is a ball, but its center may not necessarily be P. The lemma in the previous proposition doesn't say anything about centers. There were no centers in the previous proposition. But here is the point. Even if the center is not P, you can always choose a smaller ball with P as the center, which is contained in this ball. This is what we saw when we were discussing these distances. So we can choose, maybe I'll call it B prime. I'll just call this one B prime. So this blue thing is B prime. And now just choose. Let delta greater than 0 be such that the ball of radius delta around P is contained in B prime. You can always do this. You can always find such a ball. So this green thing, or at least green in this dark background video, this ball you can always find. We proved this kind of thing when we were discussing these distances. Such a thing exists. It's very simple, just a triangle inequality statement. Okay, and just call this B. Yeah, so this thing is B. And now since the F image of this guy was inside C, the F image of this guy will also be inside C. Okay, but that's exactly what this statement is. The F image of this is contained here is exactly what this is saying. Okay, so that proves 2. And 2 implies 1 is even easier, so that is an exercise. And one more thing, this may feel like maybe a complicated thing, but it is not complicated at all. I hope you are able to appreciate that. Also, this justifies the philosophy of continuity very well. What was continuity all about? that sufficiently nearby points go to nearby points. This is the notion of distance. So the nearby, this word nearby is meaningful now, not some abstract thing anymore. So when you choose a notion of nearness in the target, so you make an epsilon ball, you allow a tolerance region for the point fp. And you're asking, is there a small enough delta such that if you choose points delta near to p, you always map epsilon near to fp. So points which are sufficiently near to p map to points which are near to f of p. And that's exactly what we said continuity is all about. Sufficiently nearby points map to nearby points. Okay, so we have established the Epsilon-Delta criterion for continuity. That's a pretty interesting thing that we've done even with very little material. Okay, so we proceed. And before we look at some examples, let us look at this important fact, which can be proven using our discussion on continuity and bases. So here we have two topological spaces, X and Y, and we have a basis for the topology on Y. We haven't chosen anything for X, only for Y. So the topology generated by C is same as the topology that Y came with, and we are given an arbitrary function from X to Y. Then the following two things are equivalent. The first is that f is continuous, period. First is that f is continuous. And the second is the pre-image of any basis element is open in X. Right? So what does global continuity ask? It just says that pre-image of an open set here is open here. But when you have a handle on the topology of Y via a basis, all you need to check is for the openness of the pre-images. Right? You don't need to worry about other open sets here. And it's very easy to prove, so I leave this as an exercise. If you followed the discussion prior to this slide, this shouldn't be any problem at all. Very important that you prove this for yourself. And now we'll look at some examples. The first example, we have a function from R2 to R defined as that. So it consumes a point in R2 and just outputs the sum of the coordinates. And you should perhaps visualize this in your mind. So what you can do is you can take this horizontal thing as R2, and this z-axis is where you locate the image of a point under F. So if you choose a point here, then X plus Y may be something like that. Origin maps to origin, right? So you'll get something which I can't draw because it's a three-dimensional thing, but you can visualize. It'll look like a plane passing through the origin. It is a plane passing through the origin, the graph of the function F. Anyway, so we want to show that this function is continuous. Then F is continuous. And this is not anything surprising. Before I even comment on that, let me mention that it now makes sense to ask for the continuity of this map. We have defined a topology on R2, the standard topology. We already have a standard topology on the reals. And we have a map from R2 to R, so we can talk about whether or not this map is continuous. Now it makes sense. Okay, and such a nice function better be continuous, right? If you change the value of X slightly and the value of Y slightly, the output will also change only slightly. So the philosophy of continuity can be seen heuristically here. If you change the input a little bit, the output also only changes a little bit. That is what continuity is all about. But we need to justify this rigorously. So first let's look at the figure. What we do is we'll choose an arbitrary point A, B in R2, and we'll show that F is continuous at that point. This is not the only way to show the continuity of the function F. You may not want to give a pointwise argument. You may want to just take an open set in the reals and show that its pre-image is an open set, that is perfectly fine, but let me do it this way, pointwise way. So let a comma b be a point in R2, arbitrarily chosen. We will show that f is continuous at a comma b. This is what we want to do. Okay, so for that we'll use the Epsilon-Delta criterion. So let epsilon greater than 0 be chosen. And so once we have chosen an epsilon, what we are essentially doing is we have chosen the interval of width to epsilon centered at a plus b. This is the ball of radius epsilon under whatever distance you like, whether one distance or two distance or the infinity distance. It's all the same in the case of R1. So this is a ball of radius epsilon. And what we need to do is now produce a delta such that whenever we have a ball of radius delta around a comma b under whatever metric under whatever distance we like, all the points in that delta ball map inside this epsilon ball. So we will work with the infinity distance, right? So here what we want to do, so we want to produce a delta, positive delta, such that the infinity ball of radius delta maps inside this orange region under the function f. So without even writing, I'm just verbally mentioning that we are working with the infinity distance. Okay. So we want to produce a delta, and what delta to choose? Let delta is equal to something something. We will write that later in the course of the proof. We will discover what is a suitable delta. There are infinitely many suitable deltas. We'll just figure one out. Okay. Let delta be what we will figure out later. So now, if x comma y is a point in the infinity ball, notationally it's going to look ugly. So typically we do not write coordinates, or when we usually just write a single letter to denote a point in Rn. But here in this proof we are using coordinate notation, and which is why this is becoming so cumbersome. So if x comma y is in this delta ball, then by definition, the maximum value, or maybe I'll just write one line that both of these distances, both of these numbers is less than delta by definition of the infinity distance, and hence f of x comma y minus f of a comma b, this in the absolute value is equal to, so far we have only employed the definition of f, and now we'll use the triangle inequality. But before that, let me massage this a little bit. Now by triangle inequality, and this is less than 2 delta, because both of these are less than delta. What we wanted to do was show that this is less than epsilon. So if we just choose delta as epsilon by 2, we see that this is less than epsilon. Like 2 delta is equal to epsilon. So this thing is less than epsilon, and hence f of x comma y is in the epsilon ball, or is in the ball of radius epsilon with this as the center, right? So I'll just write one more line. All of this implies that this belongs to ball of radius epsilon around a plus b, which is nothing but that orange thing over there. Just to make it very clear, this was epsilon. Okay, so that so we have shown that the Epsilon-Delta criterion is satisfied, and hence f is indeed continuous at the point a comma b. And so we have a very nice example of a continuous function the addition function, so to say, is continuous, as it should have been. And now here is the general result that I leave as an exercise. This time we have a function from Rn to R, and it just adds all the coordinates. We want to show that it is continuous, and a very similar proof will go through. You'll just need to write a different delta here. Okay. Now for another interesting or a cousin example, equally interesting. We have a function from R2 to R, which now products the two coordinates. And we would like to show that this is continuous. Again, we have this diagram. This time, A comma B maps to AB. We will again choose, so let me write things. So let this be an arbitrary point. And we will show that, or want to show that f is continuous at that point. Okay, just restating the problem. So again, let epsilon greater than 0. And in fact, I highly encourage you to pause the video and figure this out by yourself. That is the best way to learn such things. Okay, so we have chosen this epsilon ball. And again, we'll be working with the infinity distance. All right. So again, let delta equal to something that we'll figure out later. Let delta be such that ... And yeah, so if x comma y is in this infinity ball, the one that we have drawn here, just to understand pictorially. Okay, so if this is the case, then as in the previous proof, all right, therefore this value is equal to, by definition of the function, equal to that. And here we'll play a little trick. This will be equal to, this is just a small trick. Note that this expression is same as that expression. This cancels out. So this is less than equal to, by triangle inequality, right, immediate from the triangle inequality, and this is less than delta times mod y plus mod a times delta, because this is less than delta and that is less than delta. So we have that, but since we have this inequality, this also implies that mod y is less than mod b plus delta. This is another application of the triangle inequality. This implies that. So we'll employ that here to write, which is equal to delta mod a plus mod b plus delta square. Okay. So what delta should we have chosen? So we should have just chosen a delta such that this expression is less than epsilon. So when I say delta, of course, I want a positive delta. Now, one can question, why should such a delta exist? Well, look at this expression. As delta approaches 0, this expression approaches 0. Just basic real analysis. The limit of this expression as delta approaches 0 is 0. So eventually, this has to become less than epsilon. And that's it. So if you just fix any such delta, any positive delta which satisfies this equation, we'll see that whenever we choose a point x comma y in this infinity ball, or in the picture you choose a point here, then its image will land inside this orange region, and that's it. So that proves the continuity of this function. So that's nice, and the general case again is an exercise. We have function from R into R. Fx is written this way. And we want to show that f is continuous. So that's an important exercise. And now let us do one last thing, I think. So here is an important comment. I think I've said things to this effect previously, but I can't emphasize enough. So let's look at this example. We have a function from R2 to R defined as follows. It first products the two things and then squares it. We want to show that it is continuous. And yes, you can just employ the technique or just use the same kind of idea as we did for products or sums. Meaning you can kind of argue by the Epsilon-Delta criterion or first principles. But one should try to use the more general results about continuity of a function. There are certain things that you can do, or certain ways you can break down a function into various simpler parts. And if each of those simpler parts are continuous, then the function is also continuous. So let's see what I'm trying to say. So here is what we will do. We have a function from R2 to R. First, we will consider just the product function. So let us call this function maybe m for multiplication. What does it do? It takes x comma y and products it. And then we'll have the square function. Let's call it s. What does it do? It takes a real number and squares it. Maybe z sounds odd, but what can I do? Let's say, what's a good notation for a real number? Let me just use a. Okay. But what is the combined effect of these two? Or in other words, what is the composite of these two functions? The composite of these two functions is precisely the function f. This is precisely the function f because you start with x comma y, you first become the product, and then you become the square of it. That's what it does. So f is the composite of s and m. But this we know is a continuous function. This we know using basic real analysis. And this we already proved is a continuous function. And we know that the composite of two continuous functions is again a continuous function. Therefore, f is continuous. So it saves a lot of work and makes things much clearer. If you start trying to argue this via first principles, very soon this will become a lot of headache. And more of a headache if you raise this power to higher powers. If you write a cube here, more headache, fifth power, more headache, and ugliness will also increase. But if you just use this soft way of arguing, life is much more comfortable. And we need to develop this muscle. It's easier to do this rather than argue everything from first principles. Alright, so this is all that I wanted to say. As usual, like, comment, share, subscribe, and I will see you next time.